So this is a visual depiction of an empirical method to predict climate variables a year ahead of time. So more technically what we're doing is we're using partial least squares regression to use time-leading spatial fields of climate data as our predictors to forecast a point time series of a climate variable as our predictand. So what we're doing here essentially is we're taking a time series of some predictor variable that we're interested in, like precipitation over India. And at each point in time, we want to forecast that based on a predictor from the previous time period. So in this case, we're using the global field of surface air temperature as our predictor variable. And so we want to forecast precipitation for India in each data point using the previous time period's surface air temperature. And so we would do that for the entire time series here. So this is a little bit like we're taking the time series and we're making a copy of it, and we're shifting the predictors in time and relating those to the predictands. So we have the predictors of global surface air temperature and the predictands of Indian precipitation here. And so the way that this is typically thought of, instead of looking at this in time, we look at this in terms of the relationship in two-dimensional space of the predictand, precipitation over India, and the predictor, temperature pattern from the year before on the x-axis here. So we can take these data points and compress them into two-dimensional space, relating the predictors to the predictands. And it's not typical to think of an entire surface temperature pattern as being able to be compressed into one-dimensional space like this, but this is where partial least squares regression comes in and is able to do that, where each individual pattern is essentially a linear combination of partial least squares components, and so you can actually think of this in terms of one-dimensional space here. So we hope for a strong statistical relationship between the temperature pattern from the year before and the precipitation, in this case over India. And if you have that, that means that the temperature pattern from the year before actually gives you a lot of information then on what precipitation will be the next year. But we would like to quantify how much the temperature pattern from the year before actually informs our forecasts of precipitation for the next year. And so we do that with cross-validation. We do this error quantification via cross-validation. And so what cross-validation does is you take each data point in turn and you essentially just define that as being a test data point. And the rest of the data points are then defined as training data. And so you pull out the test data point such that the statistical method is blind to that test data point. And so then it refits its statistical relationship based on only the training data. And then you can bring back in the test data point and use the statistical relationship that was only defined using the training data to make a forecast for precipitation based on the test data's surface temperature pattern and the statistical relationship with only the training data. And then you can compare that to what the precipitation was for the test data itself. So then what you have here is an error between what the statistical relationship tells you the precipitation actually should have been and what the precipitation was for that test data point. And so then you can plot that both in the scatter plot as well as in the time series data. And so then this is done for every single data point. So you can go to another data point and pull out the test data and then use the training data to fit a statistical relationship, and then make a forecast based on only the training data, and then see what the error is for that year compared to the test data, and then plot that again in time. And so this is done for every single data point. And so now you have a distribution of the actual observed precipitation over time and what was forecast for the precipitation over time based on the previous year's surface temperature pattern and not using the data from every single year in terms of the actual forecast. And so then we can summarize the actual forecast error by looking at the difference between observations and the forecasts for every given time period. And then that can be summarized by being placed by itself in its own distribution. And then what we want to know is we want to know how good this is. Like, of course, any given forecast method will produce errors. And so we want to quantify how well this forecast method is doing. And so one benchmark, one means of quantifying how well this forecast method is doing is to compare it to just the climatology of the given time series. And the climatology just means the average over the entire time period. So that would mean that instead of guessing what the next year's precipitation will be based on this statistical relationship, we guess what the next year's precipitation will be by simply guessing the mean for any given year. So the errors, if you were to do that, look like these yellow bars. So again, it would be, for this year, we're going to guess the mean as the next year's value, and so then the error is quantified by the difference between the mean and next year's value. And so we take all of those errors and then we compare them to what we had for our statistical relationship. And so you see that there's some distribution in time, but we want to summarize that over all of time. And so the typical way that that is done is with the mean squares skill score. So the mean squares skill score is that you take all of the errors based on just climatology, and you take the errors based on your statistical method, and you square those errors, and you take the mean of those squared errors, and you take the ratio of the mean of those squared errors, and you take 1 minus the ratio of the mean of those squared errors. And so that's called the mean squared skill score. And essentially what this means is that when this value is above 1, that means that your statistical relationship is doing better than just guessing the climatology for any given year. So mean square skill scores above 1 tell you that your statistical relationship is valuable and better than just guessing the average for that year.